Hello everyone, welcome to my channel. My name is Chaitanya Badodia and I am pursuing my bachelor degree of technology in electronics and communication engineering. In this video, I am going to share my experience of an embedded system internship completed through Emergy, where I learn various technical and practical concepts. This video will cover that I learned during the internship and how it helped me grow as an engineering student. So let's begin. Today we are introducing C programming for embedded systems. So C is a powerful procedural programming language. It is well known for its high efficiency and its ability to interact directly with hardware, which makes it ideal for embedded applications. This language was developed by Dennis Riches at Bell Labs. Over time, C has become the backbone of many systems, especially in the field of embedded programming where performance and hardware control are very important. Offset. C is offset called the mother of all languages, and these five features explain why it is still the backbone of modern technologies. Simplicity of and speed. C is designed to be learned and performant. It offers a rapid execution time, which is crucial for devices with limited processing powers. Second one is a structured approach. It follows a structured paradigm that promotes clear organization code. This makes it easier to manage and debug even in complex systems. High portability. C code is incredibly versatile. You can compile and run it on a wide variety of hardware platforms without major changes. Low level access. It provides direct memory access, allowing developers to interact closely with hardware, a must have for embedded development. Embedded friend lines. With its high efficiency and minimal overhead, C remains the primary language of choice for building embedded systems. Understanding the fundamental structure of a C programming is key to writing effective codes. Each components play a vital role in its executions. Firstly, header file. This file contains essential declarations or functions and macros like studio.h for head handling input and output operations. Second one is main functions. This is the entry point of every C programming where the actual execution being end. Variable declaration, defining the types and name of variables to reverse memory for data storage. Statements, these are the core instructions that perform specific actions and for the main logic of your programs. Return statement, this is used to send a value back to the callers. Typically we return 0 from main to signal that this program executes successfully. Mastering data types in C. Data types are crucial because they defines the kind of values a variable can hold and the operations we can perform on them. They are essential for efficient memory allocations and processing within an embedded systems. We use int, used for storing whole numbers or integers such as 10, -5, 0, 7, -7, etc. Float. This type stores single precision floating point numbers like 3.15, -0.5, 0.5, 0.7, etc. Care for storing the characters like Reverse for storing single characters such as A, B, 7, 8, 0. Every single character was defined by the char. Double, similar to float but store double precisions floating point numbers offering much higher precisions. Void, this represents the absence of a type, typically used for functions that don't return a value or for creating generic pointers. In any C program, we deal with two types of values, thus that change and thus that stay the same. Understanding the difference is key to writing reliable codes. Variables. Think of this as named stores location for data that can change while the program is running. They are absolutely essential for storing things like users input, intermediate calculations result, or real-time sensors reading in unembedded systems. For example, int temperature 25, etc. Constants. They are fixed value that do not change at any point during the program executions. They are perfect for defining settings or parameters that must remain static, which significantly improve both the readability and the maintainability of your code. A classic example in is const float IPI is equals to 3.1 3.14159. Operators in C, the language of computation. Operators are the special symbols that allow us to perform calculations and make decisions within our code. They are the tools we use to manipulate data and control how our program flows. We can categorize them into three main groups: arithmetic operators, relational operators, and logic operators. Firstly, we explain the arithmetic operators. These are used for basic mathematical calculations that you are already familiar with, such as addition, subtraction, multiplication, and divisions. And second one is relational operators. This allow us to compare two different values. The result is always a simple true or false outcomes. Commonly, example includes greater than, less than, and equals to. Third one is logic operator. We use this to either combine multiple relationals, relations, relationals experience or negative them entirely. These groups include logic and, logic or, and logical not. Conditional statements. Conditional statements are the brain of our program. They allows the code to execute different blocks based on whether a specific condition is true or false, which is essential for creating responsive embedded systems. Here is how we break them down. If statement. This is the simplest form. It executes a block of code only if a specific condition is true. For example, if a sensor value exceeds a threshold, an action is triggered. If else statement. This allows for two paths. It executes one block if the condition is true and different block if it is false, such as turning an LED on or off based on light levels. Else if ladder. When we have multiple conditions to check, we use this ladder to evaluate them sequentially. It provides various execution paths like turning on heaters if it's too cold or a cooler if it's too hot. Loops in C. Automation repetitive tasks. Loops are essential control structures that allows us to execute a specific block of code repeatedly as long as certain conditions is met. This automation is invaluable for tasks such as reading sensors data continuously and iterating through data arrays. Here are the three primary types of loops used in C: for loop, while loop, and do while loop. For loop. This is ideal for situations where you already know exactly how many iterations are required beforehand. While loop, the loop the loop continue executing as long as its specific conditions remains true, making it perfect for indefinite representations where the end points depends on real-time data. Do while loop. Unlike the other, these loops guarantee guarantees that the code block will execute at least one before it even checks the conditions. Functions in C, modular and reusable code. To write professional grade code, we use functions to make our program more organized and efficient. Where here are the four keys defined of using functions. Code reuse. Functions allows us to define a block or of codes once and call it mul- mul- multiple times throughout the program, which reduce redundancy and significantly improves efficiency. Modular programming. By breaking a large program into smaller manageable functions, we enhance the overall organizations, making even the most complex systems easier to understand and develop. Easier debugging. When we isolated specific functionalities within separate functions, it simplifies the process of identifying and fixing error without affecting the rest of the code. Examples: sensors reading. For instance, functions like read sensors data can encapsulate all the logics needed to interact with a sensors, making it easily callable from any part of the program whenever the data is needed. Production of arrays. Organizing your data. In the world of programming, especially when working with embedded systems, managing data efficiently is absolutely critical. Arrays gives us a powerful way to do exactly that by grouping related informations together. Collections of the some data types. An array is fundamentally a collection of items that must all share the same data types. For example, if you can create an integer array, every single element inside it will be an integer. Stores multiple values. The real beauty of an array is that instead of declaration dozens of individual variables, you can store multiple values under one single variable name. You can then easily access any specific value using its index. String communicating with characters. While we often focus on members, embedded systems also need to handle text for things like users interface or error logging. This is where strings becomes essential. Character array. At their most basic levels, strings in C are simply array of characters. Each position in the array holds a single characters, and when put together they form a sequence of text. Null terminated. A vital features of C styles string is that they are always terminated by a null characters written as 0. This special character act as a stop sign, telling functions exactly where the string end in memory. For message and display, strings are incredible useful in practical applications such as displaying status message on LCD screens, sending data over serial communications, or storing input from a user. Pointers direct memory control. Pointers are the cornerstone of low level programming, providing us with the ability to access and manipulate memory directly. In the world of embedded systems, where resources are often critically limited, mastering pointers is essential for writing efficient code. Store variable addresses. A pointer is a variable that stores the memory addresses of another variables rather than its value. Think of it as a key of a specific locations in RAM. Memory management. Pointers are fundamental for dynamic memory locations. They allows your program to request exactly how much memory it need and release it when finished during runtimes, ensuring no resources are wasted. Critical in embedded systems. They are heavily utilized for accessing hardware registers, implementing advanced data store structures like linked lists, and optimizing performance in resource constraint environments. Loop control, break and continue. While loops are great for repetitions, sometimes we need more precious control over how they behave in real times. This is where break and continue statement comes in, allowing us to alert the normal flow of a loop based on specific conditions. Break exits the loop. The break statement is used to terminate the loop immediately. Once the program hits a break, it stops the repetitions entire and jump to the very next statement following the loop. It's perfect for stopping a process as soon as an error is detected or a specific target is reached. Continue. Skip current iterations. Unlike breaks, the continuous statement doesn't exist the loop. Instead, it just skip the remaining code in the current iterations and jump straight to the next one. This is very useful when you want to bypass certain data points like skipping faulty sensors reading while till processing the rest of the loops. Why it matters? Using these statements make your embedded applications more responsive and efficient by allowing your code to react instant to changing conditions or optimize how data is processed. Basic file handling, persistent data storage. In many advanced embedded systems, there is a crucial need to store data permanently even after the device is powered off. File handling provides the necessary mechanism to achieve this enable task like data login and configuration storage. Reading and writing data. This involves essential operations to either loads information from a file such as retrieving systems configurations or save new data to a file like recording real-time sensors readings. Data logging applications. File handling is extensively used to record sensors, measurements, or significant systems event over a period of time, allowing for details analysis at a later stage. Advanced embedded systems, while basic systems may not always have full file systems, more advanced device with SD card supports or flash memory fully leverage this persistence storage capability to manage complex data. Why C is indispensable for embedded systems. To wrap things up, let's look at why C remains the preferred language for the embedded industries. It offers level of controls and efficiency that is simply unparalleled. Fast executions. Because C is low level by nature, it allows us to write highly optimized code. This ensures program execute rapidly, which is a non negotiable requirements for real-time applications. Less memory uses. C gives developers fine grand control over every byte of memory. This allows us to write every compact code that fits perfectly within the strictly limited memory resources of embedded systems. Hardware control with direct access to memory address and hardware registers. C empowers developers to precisely control peripheral and specific device functionalities. Real-time systems supports the predictability and raw efficiency of C are vital for real-time operation systems RTOS and any applications where precious time is critical for success. So let's now start the embedded systems. Let's understand what an embedded system actually is. Unlike a general purpose computer, an embedded system is a specialized computer system designed to perform one specific dedicated functions within a large mechanical or electrical setup. It, uh, it is a powerful combinations of hardware and software meticulously engineers to handle a particular task with high precision. A key characteristic is that these systems operate in real time, meaning they must respond to event and perform their operations within very strict time constraints, which makes them essential for controlling everything from home appliances to industry machineries. Features of embedded systems. In this slide, we look at the core characteristics that set embedded systems apart from general purpose computers. There are four essential pillars that defines their performance. Real-time responsiveness. Embedded systems frequently interact with the physical worlds, requiring them to provide immediate and predictable response to event. This real-time capability is absolutely critical for safety sensitivity applications. Optimized power consumptions. Since many of these systems runs on battery or have very strict power limits, their design focuses heavily on efficiency. This ensures maximum battery life and keeps heat generation to a minimum. High reliability and stability. A failure in an embedded systems can have serious consequences. Therefore, they are engineered for continuous error-free operations over long period, even when placed in harsh environments. Compact size and cost effectiveness. These systems are designed to fit into small, con- convenient space while keeping cost low. This allows them to be integrated into everyday objects without adding significant size or expense. Explore how embedded systems are classified based on their operational needs and functions requirements. We can generally group them into four main categories. Standalone systems. There are independent devices that functions without the need for a host computers. They take in data, processes it, and produce an output entirely on their own. Common examples include digital camera and MP3 players. Real-time systems. These systems are defined by strict timing constraint. They are designed to complete a specific task within very precious deadlines, making them essential for high stakes applications like medical devices and industry control systems. Network systems. These devices are connected to a network like IoT devices. IoT devices also work on the Internet of Things, such as LAN or the Internet to share and access resource. This category includes everything from home security systems to IoT devices, leveraging connectivity to provide enhanced features. Mobile embedded systems, especially found in portable battery powered device. These systems must deliver high performance while managing strict power and size limitations. Prime examples including the smartphones, tablets, and wearable we use every day. That all things are mobile embedded systems. Examine the fundamental hardware and software implements that must work together in harmony for an embedded systems to functions. You can think of these are the building blocks of the device: microcontroller and microprocessors. This is the brain of the systems, responsibility responsible for processing all data and executing the program instructions. Sensors. These are input devices that detect physical phenomena like temperature or motions and convert them into electrical signals for the process to understand. Actuators. This component performs the opposite role of sensors that take electrical signals and convert them into physical actions, such as turning a motor or switching on a light. Memory. This is where the system stores its intelligence. It uses RAM for temporary data processing and ROM for flash memory to permanently store the program code. Power supply. This provides the vital electrical energy required for every single components in the systems to operate. Input output interface. This acts as the communication bridge, allowing the systems to interact with external device or connect with other embedded systems. Heart of the systems, the microcontroller. We derive into what is arguably the most critical component of any embedded systems, the microcontroller. It is a compact, highly integrated circuit designed to cover specific operations. Here is why it is considered the heart of the systems. System brain. It serves as the certain processing unit CPU, executing the specific software instructions that defines how the entire system behaves. Input processing. The microcontroller is responsible for receiving and interpreting income incoming data from sensors and other input devices. Output control. It manages the action of actuators, translating processed data into physical actions like moving a motor or electrical signals. Integrator peripherals. To simplify systems design, it often comes with built-in component like memory, RAM, ROM and flash, timer and communication interface such as UART, SPI and I2C. It also include analog to digital converter to bridge the gap between the physical and digital worlds. Arduino Uno, a popular development board in the world of learning and prototyping. The Arduino Uno stands out as one of the most widely recognized and accessible development board available today. It is a favorite amongst students and hobbyists for several key reasons. The Mega 32-8P microcontroller. At its core, the board is powered by the ATmega 32-8B, which is a highly reliable and user-friendly 8-bit microcontroller. Easy programming interface. It features a straightforward integrated development environment IDE that makes writing code and uploading it via USB a simple seamless process. USB connectivity. This provides a very convenient way to connect the board to your computer for power programming and real-time serial communications. Digital and analog pins. The board offers a versatile range of digital input output and analog input pins allowing you to easily connect and interact with various sensors and actuators. Open source hardware and software. Because it is open source, it is backed by a massive global community, pro, uh, providing a wealth of resource tutorials and support for anyone starting their journey in embedded systems. Sensors, the system perceptors. We look at sensors which function as an essential input devices for any embedded systems. They are responsible for detecting physical quantities from the environment and converting them into electrical signals that the microcontroller can actually process. Detect physical phenomena. Sensors essentially act as the eyes and ears of the systems. They observe real world change in variables such as temperature, light, pressures, motions, and distance. Primarily input device. The raw data gathered by these sensors forms the foundation's input for the microcontroller processing logic, allowing the systems to react to its surroundings. Real world examples: ultrasonic sensors, considered HC SR04 ultrasonic sensors. It emits a sound wave and measures the precious time it makes for the echo to return. This data allows the system to calculate the exact distance of an object, which is critical features for offset uh, obstacles avoidance in robotics for modern automotive parking sensors. Bringing systems to life. Actuators are the output device of an embedded systems. They are responsible for taking electrical signals from the microcontroller and converting them into physical actions, creating motions for other measurable effects such as general motion or actions. Actuator performs the physical work of the systems. This can range for mechanical tasks such as moving a robot arm or adjusting a value to simpler actions like turning on a light or generating sound alert. Command driven output, they operates by receiving electrical commands from the microcontrollers. These commands are the result of the system's response, sensors data and following its programmed logics. Practical example, servo motor. A great example is the servo motor. Unlike a standard DC motors that just spins, a servo can be instructed to move to and hold a very precious angle. This level of accuracy makes it indispensable for robotics controlling the flight surface and remote controlled aircraft or managing camera pan and titles mechanism. Embedded programming bridging hardware and software. Embedding Embedded programming is the art of writing software that directly control the hardware in unembedded systems. It requires a deep understanding of both the software logic and the underlying hardware architectures. Language of choice C, embedded C. This C programming language remains the industry standards because it provides the perfect balance of efficiency and low level control. It allows developers to access memory directly and manipulate microcontroller registers with extreme precision. Direct hardware control. Embedded programs are purpose built to interact with the physical components of the board. This involves reading data from microcontroller pins, managing timers for precision operations, and controlling peripheral to ensure the entire system functions as intended. Efficiency and speed. Because embedded devices often have very limited memory and processing power, the code must be higher optimized. Every line is written to execute as fast as possible while maintaining the smallest possible memory footprint. Development tools. Success in this field required a specialized toolkits. This typically includes integrate development environments, IDEs, compilers, and debuggers that are especially tailored to the specific family of microcontroller being used. Ubiquitous applications of embedded systems. We look at how embedded systems have become truly ubiquitous, meanings they are everywhere, integrated into almost every aspect of modern life. They serve as the hidden intelligence across various critical sectors. Home automations home automations they power our smart homes, managing everything from thermostat and lighting systems to security cameras and voice assistants for a more connected living experience. Medical devices. In healthcare, these systems are life saving, found in pacemaker, MRI machines, glucose monitors, and even high precision surgical robots. Industry controls. They form the backbone of the modern manufacturing, controlling robotics, automated assembly lines, and complex process control systems to ensure industry efficiency. Automobiles. Modern vehicles are essential network of embedded systems, managing engine control unit, ECUs, infotainment, anti-lock braking systems, ABS, and airbag development. Aerospace in the skies, embedded systems are responsible for flight controlling, navigations, and vital communication systems within aircraft. Smart devices beyond the home. They are found in wearable technologies and smart appliances, and the vast array of IoT devices, Internet of Things that connected our world. In the slides, I am explaining my I created my project, the smart dustbins. That project is created by me, and this is the all concept applied that was I learned on this internship. And after the explanation of these projects and the embedded systems program, I will show my projects in front of you. So the smart dustbin is an innovation approach to modern waste management. This project focuses on creating the touchless, hygiene, and efficient dustbin systems using readily available components. Introducing the smart dustbin. Our smart dustbin is designed with an Arduino based systems offering a complete touchless solutions for waste disposal. This innovation addresses crucial hygiene concern, especially in shared space by eliminating direct contact with the bin. Arduino powered automations, completely touchless operations enhance sanitation and convenience. Smart dustbin are We break down the specific hardware component that form the core of our smart dustbin. Each piece of hardware has been chosen for its reliability and precious working together to create a seamless automated experience. Arduino Uno, ultrasonic sensors, two servo motors, and some jumpers wires. Arduino Uno at the center of our project is the Arduino Uno. It acts as the central processors receiving real-time data from the sensors and sending precious electrical command to the motor to control the bin behavior. Ultrasonic sensors, the eyes. This component is responsible for detecting the presence of a user by measuring the distance of an object in front of the bin. It provides the trigger signals that tells the Arduino when someone is ready to dispose of waste. Two servos to handle the physical movement. We use two servos. These are ideal for our project because they are allow for extremely precise angular positioning, ensure the lid open to the correct height and close securely every time. Jumper wires, the nervous systems. While simple, these wires are critical. They serve as the communication pathway, securely connecting all the sensors and actuators to the Arduino Uno to ensure power and data flow without interruptions. Dustbin in action, a seamless process. In this slide, we examine the complete end-to-end operational flow of our project. It follow a logic sense, think, act cycle, ensuring that the dustbin remains responsive and energy efficient. Here is the step-by-step breakdown by the breakdown of how the system function in real time. Object detections, the process being with the ultrasonic sensors which act as the system eye. It continuously monitoring the area directly in the front of the bin, waiting for the user appreciation. That ultrasonic sensors that looks on my looks on that image. This is ultrasonic sensors. And signal transmissions, uh, as soon as an object is detected, the sensors transmitters distance data to the Arduino. The Arduino immediately processes these informations to decide if the object is close enough to trigger the opening mechanism. Mm, and lead movement, the servo motors acting as the system's muscles then move the lead to a precious open positions. This allows the user to dispose of waste without ever touching a uh, contaminated surface. The two servos are added on these positions on in the bin. Lid closer. Finally, the system includes a built-in safety delays once the object is no longer detected or after a specific time. The lid automatically return to its closed positions to maintain the hygiene and keep orders content. That is my bin project was created by me. Why choose a smart dustbin? We summarize the practical value of our project. While the technology is sophisticated, its real world impact is defined by three key pillars: health, affordability, and accessibility. This benefits transforms the smart dustbin from a technical experiment into a variable product for everyday use. Touch-free operations. This is the most critical health benefits by minimizing the direct physical contact with the bins. We uh, drastically reduce the transmissions of germs and bacteria. This creates a significantly more hygienic environment, which is vital in post pandemic settings, hospitals, and busy households. Low cost implementations. One of the project greater strength is its economic feasibility. We utilize affordable and readily available components like the Arduino Uno and standard hobbyist sensors. This proves that automated high-tech waste management doesn't have to be expensive. It is a cost-effective solutions that can be scaled for mass adoptions. User-friendly design. Technology should make life easier, not more complicated. Our system is designed to be simple to operate and maintain. The automated lid improves the convention of waste disposal for everyone, particularly providing needed assistance to children, to elder or people with physical disability who might struggle with a traditional foot pedal or heavily leads.